I noticed a boring two in the middle of the day. Is that on purpose?
Yeah, I like to have it due before class and then you come to class. So as opposed to yeah, so as opposed to having it due kind of after class and you're working on it in class, or you don't come to class because you're working on the homework. So yeah, so let's get started with the class. So today we're going to talk about word like word embeddings, word kind of representations. So it's vectors. I'm not going to try and give you all the details of precisely the state-of-the-art way of doing this. This is the third lecture of the semester, really the like the second one. So it's mostly going to be here as a kind of important analogy, an important way to think about data representation, something that carries over to a lot of things. But word vectors kind of make it very concrete, and there's a kind of interesting kind of story and perspective where you see a lot of ideas in the space that developed in the context of word embeddings made a lot of sense. So that's what we're going to do today. Before we get into this, I just want to remind everyone kind of how to read the web page. Again, everything is kept track of on the schedule on the web page. The notes from that I kind of plan my lecture off of are these PDF files, which are linked off of here. And then the actual things I write on my iPad are linked off of the Scribe note there. So you can get those after class. And then the video goes to is going to YouTube as well. I think I recorded the one from the class on Wednesday properly as opposed to the one on Monday, where I didn't capture the screen next to them. And then these are more links, and this is when the homework and the project is due. So again, the first homework of the semester is already due on Wednesday. I think it's sounds like about half of you have started working on it so far from a pre-class poll. That seems pretty good. I think it should be doable by Wednesday. If the first assignment is due a little bit earlier, you can, and it's stretching it for some reason, let me know and I'll try to be flexible, but I just want to stay in our things are due Wednesday kind of schedule here. I think it hopefully is not too time consuming, but kind of gets you started on this stuff. Just to remind you about the office hours, my office hours are Thursday morning and then after class. I'll stick around after class. That we have a TA for the course who's taking another class at this time, so she'll never kind of show up here to introduce herself, but she was an excellent student last semester in the class and knows the stuff really well. Her office hours are every Monday, 3:30 to 4:30, so right after, kind of fairly soon after this this class. And then on days before assignments are due and before the tests, on the Tuesday, she'll be available as well. So this is an MEB 3105, so the big Merrill Engineering building. So this is, I think it's a shared room with other classes, but it should work out okay. So if you have kind of questions about the homework, either you can ask me or the TA will have office hours coming up. Again, it's due Wednesday before class on Wednesday. So kind of I could have it due Tuesday night at midnight, but we'll have it due on, I think it's due like 1 p.m. on Wednesday. So you can finish it and then you have time to come to class. That's the idea. You're not working during the lecture. So you're finishing it and then still coming to lecture. All right. Any questions on how all of this works? Grade scope is set up. You'll submit your grade scope, single PDF. make sure everything's labeled clearly and in the right order so we can grade it easily and we'll be happy. Again, there's a LaTeX file linked in Overleaf right here. You can a template. If last semester, a lot of students like this made it very easy, but you can, as long as it's easy for us to grade, it'll be fine. Yeah.
Like that.
If there continues to be demand for it, we'll keep doing it. It's a little bit extra work for us to do that. So if no one's using it, I might stop. But if you guys want it, I can keep doing this. Yeah, this sounds good. Okay, great. And so it was just the material we covered basically on last week Wednesday. Kind of is the point of the homework assignment. So you should have everything you need to do it. Kind of a warm up with a lot of perspectives on thinking about the randomness in data and kind of how we need to scale to large sizes and paying attention to that as we go. Okay, the other thing is I want you to start thinking about the project. The first thing of the project isn't due until September 10th when you have to turn in a proposal. Again, the proposal is like 200 or 300 words, so pretty short. I pushed the due date back a little bit, so it wasn't due like right after Labor Day. But I want you to start thinking about this informing projects. I sent out a link right before class on the Canvas announcements about you can sign up for groups, start talking with each other here and trying to form some groups. It's great if you have complementary kind of skills. Someone's really good at scaling things up. Someone else has a really good problem and they understands the kind of the aspects of the data well, right? Maybe someone's really good at building the visual aspects about it. I want you to kind of work as teams here. You'll all have to do something derived from, what we do in class in the project, but kind of when you have complementary skills, you get to do much more as opposed to you all kind of have the same skill set. So kind of, great to talk amongst yourself before class and after class and start thinking about this. And then you fill out the survey. If you fill out the survey and we get it coded, you'll only have to upload one thing for the first assignment. Otherwise, everyone needs to upload something. So start getting organized. Again, groups of 2 to 3. Groups of 4, usually too big. The chance of some group member not doing anything is a little bit too high. Groups of 1, there are just too many projects for me to keep track of. Later in the semester, I'll be meeting with all the groups individually, and I need to kind of keep that to be a manageable number. Plus, it's good to kind of work as a group on these things. All right, so I'll keep reminding you to start thinking about this. Okay, great. So let's get started here. Okay, we're going to talk about word embeddings. And kind of the key concept I want to try and convey is that it's become more and more natural. The community has kind of really kind of has really coalesced around representing data as high dimensional vectors. All right, so we're going to be going from our data X and there's going to be some raw data, and each xi will be an element here. But this raw data could be a column in a table, it could be images, it could be text, it could be a combination of these things, it could be spatial data. And what we're going to be kind of talking about today is a kind of a very specific line of work that has progressed of mapping this raw data into a vector, into a d-dimensional space. Okay, so we're going to write our data is going to be a vector. So VI is going to be VI1, VI2, VID. right? So it's gonna be represented as D coordinates. Each of these will be real values. Sometimes they're 0, 1s but we'll treat them downstream as real values, and then we'll operate on this structure. So we'll have to think about what does it mean to be a high-dimensional vector. If you're coming from computer science point of view, this is just an array. It's important to think of it as an array and not a linked list. If you're a computer scientist, the reason is if I have two vectors, Vj, J1, Vj2, up to Vjd, okay, when I compare them, I'm going to be comparing them across the coordinates. The coordinates need to be directly comparable to each other. And the next lecture, Wednesday, we'll dive into kind of more the mathematics of and the different variants of ways to do this. But with a linked list, if you change an element, it changes which coordinate is where, and then if you swap something in the middle, and that changes all these relationships, and we don't want to do that. Okay, so the fact it's a fixed size array is important. The algorithms we'll talk about today will maybe change what D is, but with every set of data, it's always going to be a fixed dimensional kind of representation. Okay, and we're particularly today interested in this representation when the raw data now, this raw data will be kind of text. And so in particular, today we're going to talk about when in fact, there are two ways of mapping text. Think of text to vectors. We'll be thinking about basically at the level of a word, right? We're going to be, and you could also be thinking about the level of a document. Okay, so I have a set of words like a homework assignment or a web page, or like a news article. I want to represent that as a vector instead of just a single word. I used to start this class, and this was kind of a traditional way of kind of from other textbooks did as well, of starting a data mining class from going from document into some other representation. What's changed is that this way that we represent words has become so dominant that how we understand, where we make sense of text, is now typically through the way we start with the word, and then we kind of just aggregate that representation to understand documents. Still, for retrieval of documents, like a search engine, a traditional part of the Google search engine, for instance, the way we handle documents going through sets and stuff is still fairly popular. And so we will come back to some of these methods as well, but a little bit later. I want to start with this one because it's really the fundamental kind of way of thinking about representing text. And also, I think it's become more natural for other things as well, for images, for like financial transactions, for genomic data. The way that is more of an analog for the word representation we'll talk about today has become more dominant than the document representation way. We'll come back to a bit later. Okay. Okay. So we'll be thinking about word from a word representation. We're going to map every word into as representing how we think of representing the base unit of text, and we're going to map that into a vector. Okay, so that's what we're going to be thinking about today, and then there'll be lots of cool things once you represent these words as vectors. Yeah, and we're going to kind of go through a historical perspective. And so the other main takeaway here, the first one is we're going to map these words into vectors, and we'll talk about that. The second one is what's called the distributional the distributional hypothesis. Okay, and this is kind of the historical perspective that tells us how we choose the vector representation of each word. Okay, how do we choose this representation? Kind of, if you think very long historical about this, kind of texts were initially kind of categorized, you can categorize words alphabetically, so you can look them up in a dictionary. And this kind of was a very powerful way for a long time. You can sort them alphabetically and you can find if a word is in a list because there's a canonical ordering of this. So, I mean, you could think of the alternatives, the alts to this were things like alphabetical. Another way of thinking about this was like the Dewey Decimal System. Who knows what the Dewey Decimal System is? It's like what's used in like a library of how they sort topics in books. You could think of sorting topics and concepts in this way. There's a huge project called WordNet. And so what this is, at least I know it best in English. I assume there's some version of it for other languages, but it's building a categorization of words based on which ones are more general, which ones are more specific. So like a dog is a type of animal. So there'd be a hierarchy where all the animals are here, and then dog is one branch of animals and cats is another branch, you know, and then there are types of dogs. There's a bulldog versus like a hound or something. And so you have different categories within here, and then there's all the verbs and the adjectives and so forth. So you could think of representing them based on the structure of how they relate to each other, which are synonyms in special cases. That's not what the distributional hypothesis is. All right, so those are kind of alternatives. This is saying that kind of words are similar to each other if they tend to have if the context of those words is similar, so how they're used is similar. So if the meanings of the words are similar if they're used in similar contexts. So think of like if you're using like a thesaurus and you want to be able to if they tend to have similar context. So if you could swap one word out for another in a sentence and the sentence still makes sense, then that probably means those words are pretty similar. Okay, so if we have a thesaurus, then it's kind of limited. These words are similar to each other. So you can like go on Google or like a thesaurus and you can hop around from one word to other words kind of by flipping through this thesaurus, and maybe it's connected. I'm not sure it is because nouns and adjectives usually don't get kind of swapped up. So it's not fully telling us a full notion of similarity between any pair of things. I want to give it a score of how similar are these words. So instead, this context is what we see, what we observe in text. Okay, this is something, this notion of context, we will define this in a couple different ways. We'll see how this is typically defined. And we can then use kind of ideas from learning and to represent the words in a way that adheres to this context we've measured from data that we have. Okay, so we want to turn this into a data-driven approach, and the representation of it will be this vectorized representations. These are kind of the two main kind of ideas. And then there was an evolution of methods of how they combine these two ideas. Okay, but these are the two kind of ideas here. And this distributional hypothesis can apply to other contexts as well with like genomics, right? If two genes appear near each other or in similar contexts, and they may have some similarity in some function or where they're represented as well. If two like financial transactions could be seen in similar contexts, then that also kind of gives an indication that those might be similar in what they represent as well. So this idea of if they can be seen and average in similar contexts, that means they probably have similar things, and we can use this to train models as these vector representations. Okay. So what this will end up leading to is we're going to get these representations of words as vectors. Okay, and this, so we're going to think of every word. So I've called this VJ, but you want to think of this as like V king. So now kind of remember how the previous lecture we said, well, we're just going to have some like large domain where J is some, so abstractly, J is an element of domain here. Well, now I'm going to treat this, this element could be the word king. King is a word here. Okay, and so there's some vector in some d-dimensional space. Okay, so this is a vector. These are vectors in our D, and we'll think of for now, maybe D will be 300 dimensions, something like that. So it'll be a vector in a 300-dimensional space for the word king. Okay, and so vectors, how do we think about vectors? There's going to be two useful kind of geometric analogies here. Okay, so let me start by, the first one is important to think of the origin here. All right, so we're in a high dimensional space and there's a 0 point here. And then the vector, this would be, let's see, V king. Okay, I can think of it as a vector from the origin. I can think of it as an arrow, right? So in physics, they tell you to distinguish these things. The other one is as a point. Okay, the point makes sense if I have V, if this is equal to kind of 1 just in 3 dimensions, 3 kind of 2, then I would think of, well, the first coordinate here is 1, the second coordinate here is 2, or is 3, and the third coordinate here is 2. So these are axes, 1 along the first axis, 3 along the second axis, 2 along the third axis, right? But this could be a 300 dimensions. I can't draw pictures and all these things. This arrow representation is capturing the same thing. For us, it's not going to matter. We're going to kind of sometimes go back and forth between these representations, thinking of an arrow or a point with coordinates, Cartesian coordinates. Okay? Or if you can think of it as an array, if you like that as computer scientists, then that's fine as well. Okay? Okay, so I can do multiple of these vectors. So what's interesting is when I put them together in the same space, this is the vector for king, this is the vector for queen. I can also do things like this is the vector for man. Okay, and there turns out, and this was surprising, this was not kind of intentional necessarily, but what they discovered with these representations, there tended to be these linear relationships where I could look at the vector from king to queen, and I could take this vector and I can add it onto man. And then I could look in this neighborhood. Let's look in the neighborhood of what was added here. And it turned out it was often the most the most similar word to this endpoint might often be, like in this case, the word woman, because what I've done is I've taken this king to queen vector, which is implying some gender information, somehow is capturing that, and I translate it onto the man vector, and I translated from man, the male to female aspect of this, and it would tend to find the similar word would be woman, and these kind of analogies kind of emerged from this representation unintentionally. I mean, maybe they had the foresight to do this and they realized it kind of soon after, but this was kind of this really neat phenomena that kind of showed up, that these linear properties were kind of showing up here. You can also see that there seems to be some sort of some royalty vector that's also going in, or in this way. The reverse of this would be taking a regular person and adding a royalty term onto them. So if you took boy, it might map to prince if you did this as well, or girl to princess, perhaps. Yeah, go ahead. Yeah, great. This is a great question. That's what we're going to talk about most of this lecture. I just kind of want to give you some geometric sense of why this is a useful thing to do. Yeah, so great. How will we get these vectors for these words? That's kind of that's the big question here. And that's what's evolved and caused a huge amount of advancement in AI in the last kind of 20 years, the story will be about. Yeah. It could be around here. There's probably another vector that's translating from nouns to verbs, right? Or nouns, a different one from nouns to adjectives. And this, it's a high dimensional space. And I can't draw all the relationships at a time, but kind of each of these kind of concepts from one, maybe encoding gender or royalty or to nouns to verbs, is there's kind of a subspace representing this. It's not always one dimensional. We'll kind of talk about this. And I've kind of through a lot of my research, I've been trying to explore how much of this actually is linear and how much of it is kind of people find linearity because they're looking for it. It's not necessarily there. But these sort of analogies actually worked. And at some point, I think there were these people were trying to solve these questions from like the SATs and stuff, and you have to do analogy questions, and they use these representations, the kind of the second generation of them, to try and solve analogies by just doing king is to queen as man is to question mark, and then getting this vector and finding the nearest neighbor. And this worked surprisingly well, right? It wasn't quite like probably as good as all of you were at doing it, getting into kind of a good university, but it was quite surprisingly good. And I mean, now these things are even better, but probably because they've looked at all the questions. But that's another story. Okay, so to kind of maybe make this concrete, I added a link to this demo right here that I found. This is somewhere hosted at CMU. My research group had built something like this, but it's kind of, the grad student graduated, it's kind of deprecated, but this one works pretty well. They have embedded a bunch of individual words here, and they've drawn it in a three-dimensional space that I can spin around here. And so we can always see two dimensions at a time. And they explicitly tried to encode one axis as the gender axis. So if I line it here, a bunch of the definitionally male words are on this side, definitionally female words are on this side. They also have an age axis. Yeah, so you can kind of see it here, the kind of adult words, father, uncle, king, man, wife, aunt, mother, woman, queen are on the top. And the children words, nephew, prince, boy, girl, princess, daughter, all on the bottom. Okay. And then they have some residual other axis where other words like chair and computer. Again, these are all nouns, but you can put adjectives and adverbs in so in here as well. They will embed someplace in this space. Yeah.
So I don't know if you want to go. Why was there a big difference in the male and then the word husband was seen more on the feminine side as far as their data set? You know why that is?
Yeah, so these embeddings are kind of, and when you try and look at this, it's kind of noisier than you would expect.
Okay.
I don't actually know what's the back end here. Like mostly when we were using these word vector embeddings that these are based on, we were to do any analysis, we use like 300 dimensions, but our demo that we had built used only the 50-dimensional version because the space was 1/6 of the size. And the data sets are big to load on a web thing. And so the 50-dimensional one was much noisier than 300 dimensions. But even the 300-dimension one, there's the stuff that ChatGPT is using now is much higher dimensional, much more complicated than this. And it take a long time to load in the demo here. So these are just not perfectly aligned. They still work pretty well, but they're kind of a noisy process. They're only as good as the data they trained on and the amount of training you did, and maybe some other things. But so conceptually, it mostly works. But again, yeah, the embeddings are not perfect here. It's not, if you were to try and place these yourself in here, you probably could do something better for just this set of probably like 10 to 20 words that they've done here. You could probably come up with even better coordinates that you thought represented it better. But these were learned automatically, and they work kind of not perfectly all the time. For instance, one thing we looked at with this was, if you're trying to get beyond about this set of words for male and female definitionally words, you can use words like he and him and his, but after about 20 words for both male and female, you start to really run out of words to use. You can use like if you want to stay in royalty, you can go with like Duke and like Duchess, right? But Duke mostly shows up as the university, not as the Duke who is the kind of part of royalty. And so its embedding is not where you would expect it to be looking at it in this context, because these words are assigned have other context and meanings other than what you're probably thinking about here. So it's challenging to figure out how to get this to work. Okay, but this was kind of the second generation of things. So let me kind of and you can look at this and play with this, and we'll actually plan to come back and talk about some of the bias and these other issues later in the semester. So we'll think about what does it mean to use these sort of automatic representations based on all sorts of other issues later on. Yeah. Oh, the color scheme on here. Yeah, so this is a visual representation of the vector. I'm guessing they are using a 300-dimensional representation based on this index. This is kind of think of this as the array, a 300-dimensional array, and the values tend to go from -0.2 to +0.2, and they're color-coded, so you can see that queen and woman both have a thick blue part here, so they have a bunch of coordinates that are all positive, and they have, some other similarity here. There's a lot of similarity between these vectors, but maybe you can kind of think about adding and subtracting this to do the analogy. How you would do that analogy picture I drew on this slide is with vector operations, where I'm actually king minus queen. This vector is queen minus king. That represents another vector, and then I add it onto the man vector. I can do those as vector operations, which are element-wise operations. And so I can see all of those elements right here. So I could think of doing these operations on these vectors. And so if you kind of play to it, that should kind of check out, that the analogies kind of would work out. I don't know how to see it so cleanly here, but okay. But you can link to the demo, you can play with it. There's some other functionality I won't kind of go through at this point. But if you want to kind of get a sense of these things, it's a cool thing to look at. All right, so let's get onto the big question: how do we get these vectors, right? So I don't want to just encode them by hand, because as I mentioned, there are something like, what we'd like to do this for m equals something like 100,000 words. Okay, I'd like to find a representation that works for 100,000 words, and this would be a lot to do by hand. Okay, so I somehow want to automate this, so not just those easy to understand vectors, but every single vector I can put in there, I can look up and I can plot it and understand its context based on how similar it is to these other vectors. Okay, so let's use as a word the word equals like octopus, for instance. Okay, so in order to do this, I mentioned we need to use this distributional hypothesis. So I need to, and to do that, I need to define the context. So you have to look at all the places, and so we're going to have some corpus of text with kind of n words in this. Okay, a small example of a corpus of text that's commonly used is all of Wikipedia, all of the English language of Wikipedia. This was kind of the smallest data set that people got this to run on. That sounds pretty big if you haven't dealt with it before, but that's a small data set. They would try to run on there's something called the Common Crawl, which is like trying to a documentation of what all the web pages on the visible kind of internet were. So all of Wikipedia, but my homepage and your homepage and any homepage that can happen. This was kind of before Facebook got too popular, so people mostly posted their own HTML pages since it was easier to scrape these things. Okay, so we have a corpus of n words in text, where n will be much bigger than m. N could be in kind of think of billions, hundreds of billions, maybe. And so then there would be some part of this text would be someone saying, I saw octopus kind of teacher. This I saw Octopus Teacher this weekend. It's a movie. And so the word octopus occurs somewhere inside of this long string of text, right? So we have this word octopus. There's going to be kind of another sentence, kind of the kind of large octopus ate the large octopus ate the fish. Okay, so you also see the octopus in this context. There might be other sentences before it. There's a bunch of modeling questions. Do you merge the sentences together? How do you model punctuation, capitalization? Maybe this should have been capitalized. Does that matter? Okay, initially they did not want to worry about these capitalization and punctuation issues. Okay, so now we define the context, and typically they would do this by looking at some window around the word that was 3 words, let's say 3 words in either direction. So if this one kept saying ate the fish at the zoo, right? Well, then at the zoo is outside the context window. I only looked at a context window, say, of size 3. Okay, and so this is the context of the word octopus. Okay, so and so you can see from the context, you can imagine that if I saw octopus, that might mean that octopus is either an adjective of something or is kind of a noun itself, or is somehow the subject is after here. Maybe you could infer that the large octopus, the large is a modifier, then octopus. So it's probably you understand something that it's some object. And so that's captured somehow in the context. The fact that it's near ate the fish means, okay, it ate the fish, maybe it has something to do with the water and sea. You start to see how the context is somehow telling you something about the word octopus. Okay. kind of there's a longer history of this, and the natural language processing used to be much more detailed in modeling the sequence and breaking down sentences into different parts. Now it just says, let's look at this neighborhood of 3 words on either side as the context of this word. Okay, so how do we represent now octopus as a vector from these words, but maybe it appears a whole bunch of times in the text? I want to keep some statistics on pairs of words. Okay, so I'm going to keep a kind of a co-occurrence kind of vector. Okay, so we'll say that I'm going to keep a co-occurrence vector bj, and this is going to be in rm, and again m is going to be 100,000. This will be the first generation of these things, of these word vector representations. And this co-occurrence vector bj, and here the idea is that the index j is representing the word octopus here. Okay, and so this vector is going to have bji is going to be the number of times word j has word I in its context. Okay, so I'm going to look at all the instances of the word octopus and count how many times the word, let's say, the appears in the context. In this case, I see it appearing twice in the same thing. So I would increment the counter b octopus the bji to be 2 because I saw the word the twice. The word large appeared once. I would increment this counter. Okay, this is a vector representation, but it's not yet a useful one. Okay, the word the occurs in a lot of contexts. So the fact that the word the b octopus the value is large is not really telling me too much. Okay, so I also want, I'm going to want to kind of update this in a couple ways. First, I'm going to create a probability. So this will be PI, and so this will be the equals the number of times word J, PJ, word J occurs, and divided by n, this total number here. And then I'm also going to have P I J, which is going to be Bij divided by n. Okay, so now I'm saying the count of the time that the words appear together divided by the total number of things here. So this is Pj, this is Pij. So I have a probability based on just the probably the word j occurs in the context, or out of all the words, the probability I see this particular word, and if I draw a random word from my corpus, and this is that the probability I see 2 words together. And if I'm being really careful, I should maybe normalize by the size of the context window to think about the meaning of these things, but that'll be the same for everything, and it will kind of factor out. Okay, so this is almost useful here, but I want to kind of look at, I want to kind of consider what's going to be called, let me put this on the next slide here. Copy. Okay, what I want to see here is kind of so I want to define something called the pointwise mutual information of I and j. And so this will be the log of Pij divided by P of I, P of j. Okay, so if they occurred together in the same context much more than I would expect individually, just like the probability I occurred and the probability j occurred. So if I pick two random words and I and j, or if I pick two words and say, what's the probability I picked this one and this one independently, and this is the probability I saw them together. So if they have a high pointwise mutual information, I see them together a much more than I would expect if it was completely random. That's what this is saying. Okay, and so finally, I'm going to assign a vector Vji is going to be equal to the max of 0 and this pointwise mutual information, Pji divided by Pi times Pj. Okay, so if the ratio, if I see it less likely than I would expect, then this ratio is less than 1 and the log term would become negative. I round that down to 0. What this does is that my representation, if it's unlikely to be seen together, there's no positive correlation, I mark it as 0 and the vector becomes very sparse. So this representation is mostly zeros. Most stuff I see about as much as I would expect or less likely than random. The ones that I do tend to see together, it gets a positive score. And the log means if the ratio is really big, it grows kind of slowly. I don't want to get too big values here because if something rare happens, I don't want to get too excited based on something rare. So the log kind of is tempering this a bit. Okay. Also relates to entropy and a bunch of information theory of why the log is showing it. Okay, so this Vj vector, this gives me a vector Vj, again for the word octopus, would be Vj1, Vj2, up to Vjm. Okay, so now I get a vector representation for each word in this m-dimensional space. A lot of the values are 0, so it's pretty sparse. So if I use a compact representation, it may not need to be 100,000 dimensions, but it's still pretty big to store. These are pretty big vectors to deal with. I was complaining before about 300 dimensional vectors for the demo we built 5 or 10 years ago. Now this one was using 300 dimension. 100,000 dimensional vectors are just a pain to work with. Okay, but this was kind of the first generation of how we could represent text as these vectors. Now, if they occurred in similar contexts, they're going to have similar J and J prime, two words, octopus and squid, are probably going to have similar other words that they are likely to co-occur with. And so if I measure the distance between these two vectors by comparing their entries, I'll be able to kind of understand kind of how similar are these words. So think of it as a representation of it where I can do a bunch of pairwise comparisons to kind of measure how similar they are. But it also has this vector context where I can start to draw these geometric pictures, right? And I can do geometric operations, and throughout the semester, we'll be doing lots of kind of geometric operations within the context of data mining. Okay. So these were not directly commonly used, but this kind of modeling of the words became important for the second generation, which is where this demo came from, and then led to the third generation, which is what these large language models are based on. Okay, so what was actually used was kind of fairly similar to this. There's a notion, thing I'm not going to describe here. It's very similar ideas were used in document representation, where they're used like term frequency inverse. So inverse document frequency, TF, IDF, and it's similar to kind of weighting these terms based on how unexpected they are. It's not exactly the same way of building this representation, but they built similar high dimensional representations for some documents based on which words or kind of sets of words, these k-grams, as we'll see in a couple weeks, how unexpected they were in the document. And so there's this really old software. So this is similar. Let me say, so this is similar to TF-IDF, which is term frequency inverse document frequency. And this is basically the model of this method called BM25. And this is still hard to beat for information retrieval. About 30, 40 years ago, a couple of professors in England came up with this way of weighting things and representing these document vectors. And it's still a baseline that you can't, in some data sets, it's still the best way to do it. It's based on this sort of idea of representing every possible word, and how unexpected is it is kind of its representation. Very high dimensional vectors. You have to have compressed representations, but this has kind of been a baseline that still works kind of well in some contexts. Okay, so even though this seems, I don't know what your impression of it, but this gives you a way to generate a vector representation. Hopefully that kind of makes sense here. The next ways will be even more abstract than this, but this kind of gives you a concrete way of defining every coordinate of each of these things, and it's learned from the data. I just give as input this large corpus. Think of all of Wikipedia, all the text on the internet, including Reddit and who knows what. I can just build these patterns of these contexts of each word, and I can turn it through this process into this pointwise mutual information vector, and this directly gives me the representation. It's super high dimensional, but it's a vector. Okay, and that's kind of what we need to make a lot of the machinery work. Okay. Let's talk about the next kind of advancement. The next kind of phase of things kind of took advantage of self-supervised learning. Okay. So I talked very briefly in the very first lecture, the kind of overview lecture, this idea of supervised learning. And I said we weren't going to do supervised learning in this class for the most part. Right? Do you remember what supervised learning was? Remember? Learns from the data. How does it work? What do you need with the data? It has a data and a label. Yes. So supervised learning is when I have I have a data set, and each one is a label. In this context, maybe we think of it as +1, -1, right? Either positive or negative, and then I can fit a pattern to the data for every data point is paired with a label so that it kind of aligns with the label. And I have to be given all these labels as part of the input. Okay, and so when I was in kind of when I was in graduate school, 20-ish school and graduate school 20-ish years ago, people knew how to do supervised learning, and we were realizing data was getting very, very big. Usually these labels would come from experts. Okay, so an example would be you have a medical image and you get a doctor to label it, this is cancer, this is not cancer. Well, if you've ever been to the hospital, especially if you didn't have great insurance, you know, doctors' times are very expensive. And that's generally true for experts. So it was very expensive to get good labels on these things, but we were getting lots and lots of data without labels, and we didn't know what to do. And there were lots of proposals, and a lot of the proposals from when I was in grad school turned out not to be what is the method that everyone uses now, which is self-supervised learning. Okay, and this is really what allows us to kind of go to a learned representation of the data as opposed to kind of an encoded one like this one. This one is kind of directly read off kind of algorithmically from the data. If I update one word, I kind of can figure out exactly how it's going to update here. I want to somehow learn a lower dimensional representation that is maybe capturing similarity even better than before. And I want to somehow learn something, but I don't have labels on these two words are similar to each other. Maybe I have the source, but I don't want to use the source because I want to understand how to place share with the word whispering. I want to have all words in the same context, you know. I don't want to rely on labels here, which is kind of what a lot of the previous mechanisms in language modeling had done. So what this is doing is this context, when I have this context, say the fish swam away from the octopus right to the shark, right? So I have this sentence in this domain. I have the word octopus, and so I have information about each of these words right here in this corpus. It's not telling me a label how similar they are, but this context is giving me some information. In fact, what it's capturing is what is examples of English language that's for the most part properly written, right? Not all the language on the internet is properly written, but say the New York Times articles or Wikipedia, it's pretty good, right? And so it can learn to understand kind of how language is structured and what words are similar, the context, right, might be, right, the context of the word is right here. I somehow want to use this in order to the labeling. So the idea is I did not need to explicitly label it, but every object I have, the word octopus, has some natural context to it, and I somehow want to use that to learn to it. So you could think of a similar thing if you have like an image, and you can learn image embeddings as well by masking out part of an image and trying to predict what should be in that piece of the image that you took out that's missing. You have a string of stock prices or of a string of sequence of like financial transactions. I take one out and I look at the ones around it, and I can try and predict what was that object that was taken out. Right? I could think of have a log file. Right? You're running some program that's doing some weird stuff, and it's spitting out a log file of all the steps you did. I can predict what should have been a log file that I left out based on the ones around it. Right? You get these sequences of data. And this allows you to kind of understand what is the pattern of things and to kind of understand to predict what word is missing. Yeah.
Could we use this for imputing missing values?
Yep, that's kind of how to think about what's going on here, right? So what I'm going to do is I'm going to mask out the word octopus and then use the words around it, whether it be a size 3 context window or something else, to try and predict what word should be here, right? So it could be away from the squid or octopus or whale but it's something that's under the sea in this context. Okay, could be the boat, so, but it's, you kind of get a sense of from the fish and the swam and the shark that, maybe not from the 3 words on either side, but if I expand it to 5 words on either side, I probably get a good sense of what's going on, right? How big should the context be? Well, we'd like it to be larger and larger context, and this will be kind of the last part of the story. Okay, so what I want to do is to mask out a word J and use the context to predict its value. And because I had text, I know what the right answer is, right? So I want to predict it, and if I predict the right thing, think of like with if you know how kind of stochastic gradient descent works, if I predict the right thing, I don't have any penalty. If I predict the wrong thing, I get a penalty, and that back propagates through some kind of network representation. Okay, and so I can use the context to predict the word J, and if I get it kind of, if I make the wrong prediction, then I have to try and update my representation a little bit so it's more likely to predict the right word. Okay, and ultimately, there's going to be some large kind of neural network that is going to go to a representation that's going to be in RD, let's say 300 dimensions. Okay, and this is going to be the output of, not quite the output layer, but the last layer of the neural network is going to be 300 dimensions. Somehow going to take in a sequence of text and get here. And then it's going to compare this kind of the activations here. It's going to look at the activations dot product with the word J that's supposed to be there. And if this is the largest value of all the words in the data set, then these are the most similar, and it's going to choose the word VJ, and it doesn't get a penalty. If it chooses the wrong word, it's going to try and move this representation based on the context, right? So this context, this is the context. And so it's going to get this word representation A. If the context is not aligned with it, then it's going to move it towards this the representation of the word VJ, where it moves the representation of the word VJ closer to the context that was how it was represented here. And this is kind of how the neural network works at a very high level. How did it pass the context in here? The initial methods here use these LSTMs, which was a method designed for neural networks that try to look at sequences of objects and long short-term memory, and tried to pick out the words that were most relevant and weight them higher in this context. But it's not so important now. Okay, so this is kind of how this worked. I have every time I saw the word in the text as I'm going over, I pass it through the representation. I check against the vector representation of the word with the dot product. And if it picks out the wrong word, it's similar to the wrong word, it updates the representation of this word that it saw. This vector, VJ for the word, which is also 300 dimensional. And you just keep iterating this, and the words kind of move around in 300 dimensional space until this prediction improves. Okay, so there are lots of details of how to make this work, but this is kind of the high level idea. It used the self-supervised learning to mask out a word and use the context to try and predict what its value should be.
So would it do this for every word in a sentence, or would it just take a sentence?
Yep, it would do this for every word. Think of it as scanning over the text and keeping track of the context, and then updating it one word at a time and shifting the context windows. And so think of you're reading through the big corpus, and you keep updating all your representations by passing them through. Right, so you want to be able to train efficiently. You want to read as much data as you can and train with this as fast as you can. Then there's things about doing it in parallel and parallel stochastic gradient descent and it's optimized over a bunch of stuff and it mostly works out. Okay. One thing this moved towards is thinking about the context here. Instead of looking at both sides, eventually this moved towards the context. I wanted to make as large as possible, but I only used the previous text to predict the next word. Okay, so what this eventually, a lot of this started out where the context was on both sides and said, well, we can kind of get this to work if I only use the context on just one side, right? So I've got a sequence of text here, and what I want to do is the next word prediction. Okay, so I have a sequence of words so far. The fish swam away from and then it has to predict what is the next word, right? And it's using this neural model to do this. It gets to this activation at the end. It looks for the closest word. That's the next word it predicts. And so this is the next word predictor. When I was an undergrad, and maybe some of you had to build this program yourself, we had to build a program where we took up one of these open access books like The Man on the Sea, Old Man on the Sea or something, and then build a model by looking at every 2 words, what's the distribution of what the next word would be. A very simple model where we looked at 2 words and predicted the next word just based on counts in the book. And this is just a complicated version of this that instead of just keeping counts, it's building a neural network in order to estimate what the next word would be. But it's not too different from how these language models work at a very high level view. Okay, it's just doing next word prediction from the context being the sequence of words leading up to this point. I'm going to predict the next word. And if you run a large language model like this, it will output text and it will look kind of like English. All right, and this, just building this on yourself, you could probably build this and you'll see something that it won't really make logical sense so well without doing a bunch of other stuff that's happened in the last 5 years, but it will look kind of like English. Yeah. So when I did this with the small book, because this was a long time ago and computers were much slower and more expensive. And so it would not have been feasible to run the code I wrote back then on the computer I had then on all of Wikipedia. Now you could definitely do it. This would not be, you could write this, and you could probably write this if you're good and you're using AI probably in the afternoon, and you could build a next word prediction on all of Wikipedia and train this, and it would look like English. The sequence of words would look like sentences, and they could probably get it to put punctuation in and figure that out. Not too hard to do. It won't work like a chatbot yet. There's other stuff that really needs to go in there, but it will work pretty well for looking like the patterns of grammar you see in English. It won't be able to tell a coherent story or something like that. Imagine this game where you go around the table, everyone has to say the next word, and you're kind of making up a story as you go. It'll kind of be wild like that. It won't really keep a lot of sense of what it's trying to do, but it will sound like grammatically like English language pretty well. And locally, within one sentence, that might make sense. But if you string 3 or 4 sentences together, because that goes outside the context window, it changes the subject and stuff like that. All right. So this was kind of, okay, so this was basically how they built these 2 methods called, this led to around 2013 and 2014. This led to 2 models, Word2Vec and so in Glove, this came out of Google, and this shortly after came out of Stanford. I linked to Glove. It's got some nice resources. You can download the word vector embeddings of different dimensions for up to 50 or 300 dimensions. Learn from Wikipedia, learn from Common Crawl, which is kind of all the internet. And you can play with them, and they're pretty easy to play with. And I'll probably give you an assignment to play with one of these things if you haven't done before. But they're really easy to work with. Okay, and that's one of the beauty of them. They give one vector representation for each word. Okay, and they fixed in embedding representation. When these were introduced, a bunch of long-standing benchmarks that people have been stuck on from natural language processing started to be improved. You could use these as the initial representational language, train classifiers or analogies on top of them, and things just started to work much better. Kind of, people were very, very surprised about this. I had a couple of issues though. It was not perfect, and the main one is that each word has one representation. Okay, so what happened is that the word bank, right? Bank could be the bank of a river or a place where you store your money, right? And they're both nouns, but they have very different meanings and context. But there's a single representation for the word bank, right? And there are a lot of words that have multiple different meanings, but each of them had exactly one representation, right? So if you think of the word king, there's King Charles, there's and then there's like Burger King, right? Those are, I won't comment on how similar those are, but like there are different representation of these words, but they were forced to have one representation here. And how to disambiguate these was not clear. There were a bunch of kind of hacks that came along. They tried to identify these or learn these different representations. So, but this was kind of the state of the art for about 5 years or so. And then in 2019 or so? Do you remember when around 2019 came out this approach called ELMO, which is out of University of Washington and Allen Institute for AI. And they said, we're instead going to build a function, and the function is a neural network that was the context plus the word, and this mapped to a vector VJ for the word. Well, let's just say just a vector which is now in a d-dimensional vector. So it mapped for every time I saw a word in a sentence. Usually I was using these to analyze a string of text. So I would take the context with the word and embed this as a vector. The context would tell me which meaning of the word bank. If I swam to the bank of the river, if I swam to the bank, I probably wasn't going to swimming up to the front of a bank to deposit my money. I was probably the bank of a river, right? And so I could know from the context which the meaning of the word was. And this didn't mean it was only one location. It could subtly change based on the context. Most of the representation was the word itself, but I had some part of the representation from the context. So it was still learning a neural network that mapped every word, but it wasn't a fixed representation. Okay, this was a multi-layer neural network. The first layer ended up being like the glove representation. But the next layers gradually included more and more context about it, this multi-layer neural. This still used this LS, which was kind of, didn't allow the context window to be too big. Soon after followed this method called BERT, which was out of Google. And it had the same functional representation of a word, The big difference with this one was it used a transformer network, which has this activation at every layers. Okay, so this attention mechanism at every layer. This has this attention. This attention is all you need. Paper was very influential. And what it allowed it to do is to have a much larger context. And this attention mechanism did a better job of picking out the relevant words in the earlier context. Now you could have hundreds, or some places have thousands of lines of context for each word representation. So the transformer and the attention mechanism allowed the context could be much bigger. Also, Google had a lot of compute resources to train this on. So you could train with really big context, train a very big model. This theta is all the parameters in the model. Was it billions and trillions of parameters in these neural networks, and large data sets passed into these. Now I have these functional representation of every word, mostly depending on the word, but some on the context that tell me about it. And in fact, with the transformer and the intention, it's layering, it's kind of layering the context on top of the representation over and over again. So it's kind of just updating the context of every word to know what the conversation is about, but then where it is in this kind of sequence of text to predict better what the next word should be. And so these mechanisms with these kind of contextual embeddings and with these transformer and attention models, which have very large context windows, are really the backbones of these large language models. Soon after this, kind of OpenAI and other places started training as much models data as they could on top of this, and mechanisms to kind of train some reinforcement learning on top to make sure that they were actually answering questions in like a chatbot. But this is kind of really, I think, the foundation of what makes this work, and a lot of language modeling, kind of language understanding works, is based on these mechanisms. Okay, it's a little bit more complicated. So now the word's representation depends on the context and the word. So you can't describe, okay, here's a big data set of all the representation, all the words. I can't show you that demo anymore for just individual words. I have to depend on all the context. So it lost a lot of intuition. So I think for this class, we'll often go back to kind of this representation where we have a single kind of a word has a single kind of vector in it to think about it and to use as kind of a proxy for lots of data is often embedded in this way. But know that this next level of things, which adds complications and removes interpretability of what's going on, is kind of led to all these advances in large language models. Okay, so this lecture again was not meant so you'd have a complete understanding of how all this stuff works. It's meant to kind of give you a way to think about why it's important to, or how we can learn these representations of all sorts of data as these high dimensional vectors. Okay, the next few lectures we'll talk about, okay, now that I have high dimensional vectors, what are the base measurement of operation on these vectors? And these are going to be notions of similarity and distance on top of these vectors. Okay, and then once we have those, we need to be able to work efficiently with similarity and distance, finding the nearest neighbor among things. Remember this operation with the analogy, I could do queen minus king, add that vector to man, find the nearest neighbor in my data set. I have to be able to do this operation, but in 300 dimensions. Okay. Again, when I went to grad school, I was told you can't do this efficiently. Now that's changed. We can now kind of quickly find the nearest neighbor in these representations. So we'll have to talk about this. And then we'll talk about some alternative modeling of language and text, kind of to wrap out this unit. But this is kind of where we are in this pipeline of techniques. All right, so any questions before we wrap up or finalize? Some people seem very eager to get going. So so great. So okay, well, before you leave, chat with people about project partners. You still have a couple minutes here, and start thinking about forming your groups. And then I'll make sure to finish your homework. It's due at 1 p.m. on Wednesday. So if you come to class, it's not done. It's already a little bit late. All right, well, we'll stop here.
So are we not gonna learn about like transformers and stuff like that?
I am not going to be able, let me figure out how to pause the
Or is it just like the build up to that?